Hello viewers, welcome back to this channel. So in this video we are going to be handling the introduction video about electrochemistry. So we are going to cover this video in parts like we have been handling other topics. Now just like in the previous video, we said that the concerns are going to be submitted over WhatsApp group, and we made the link for that, which is also going to be linked in this video. So in case you're not part of that video, try to clog my inbox. You present your issues under that platform. So in this video we are going to be starting one of our last topics under physical chemistry, which is going to be talking about electrochemistry. So this video is suitable for students that are going to be in senior 6 together with the coming senior 5, though the presentation is going to change. So this video is presented to by Ogembe Yusuf, and your advice subscribe to the channel and share the video to your friends so that you can all benefit as a group. Now talking about electrochemistry, we are going to look at electrochemistry mainly introduction, where we are going to be talking about mainly electrolysis. And in the coming videos we are going to go deeper, but this video is suitable for covering electrolysis as one of the introductory subtopics under this branch. So electrochemistry as a branch is going to be the chemistry. We are going to be dealing with the chemistry that is going to deal with chemical changes that are going to be produced by simply passing electric current into a chemical system, and this could be a molten substance or simply a solution, and this is done by the aid of electricity by spontaneous chemical reactions. And we're going to cover all that under this topic of electrolysis. Now just to make a review, if you lack anywhere, I've said that you are going to submit your issues or concerns in that WhatsApp group. So if you lack anywhere, make sure that you present your issue in that WhatsApp group, and then it will be worked on. So looking at electrolysis, we are going to say that this is going to be the decomposition of a compound present in its molten state or in its solution state simply by passing an electric current through it. So just like you looked at it in O-level, electrolysis is simply decomposition of a substance by passing an electric current through it, and that's a simple definition. For as long as that substance is either present in the molten state or it is present in solution, because electrolysis is very impossible with solids and gaseous compounds. Now you're going to be looking at the various electrolytes that you can put in our electrolytic cells, and you're going to look at the strong electrolyte together with the weak electrolytes. Just like the strong acids and the weak acids, we are going to define electrolytes the same way. So strong electrolytes are going to be those electrolytes which almost completely ionize in solution, and their solutions therefore do not contain unionized molecules. So a simple definition for strong electrolytes are going to be those compounds that are present in molten or solution states, but in solution but ionize completely. You may leave out the word almost, but ionize completely to form their respective ions in solution without leaving any unionized molecules. So the examples of that, you're going to see salts, strong acids together with strong alkalis, as these ones, they all ionize completely. Now the weak electrolytes is going to be the opposite of the strong electrolytes, where we are going to say that weak electrolytes are going to be those electrolytes which partly ionize in solution, and therefore their solutions are going to contain ions that are present in equilibrium with the unionized molecules. So they are going to include most of the organic acids, and then together with bases and ammonia. Now ammonia is the only inorganic base that is a weak electrolyte, but others are going to be organic substances. Most of the organic acids are weak electrolytes, as we are going to be looking at that in details. So in this table, we are going to first look at the examples of the electrolytes that we are going to be dealing with. Just like we said that strong electrolytes are going to be mostly ionic or inorganic, and then the weak electrolytes are going to be mostly organic. or ammonia solutions. So for example, we can have some of the strong electrolytes. We have sodium chloride. You notice that the strong electrolytes are going to be formed from a strong base together with a strong acid. So sodium chloride, just like we looked at them in ionic equilibria. So under strong electrolytes, we are going to have sodium chloride, calcium chloride, sodium hydroxide together with hydrochloric acid. All these ones ionize completely in solution to give us their respective anions together with the cations. That means that when you're writing the equation for their anionization, the arrow must be a full arrow. Now, if you go to weak electrolytes are going to be mainly organic, though we have some few inorganic. Now, here we mentioned carbonic acid, but carbonic acid, we don't have it in the laboratory, and it's very hard to get it at room temperature. So this one is very rare. But most of them we have ethylamine, which is going to be a weak electrolyte since it's organic. Ammonia solution is inorganic, but it's a weak base, together with ethanoic acid. This is also a weak acid because it's organic. Now, having looked at electrodes, let's look at the definitions or the inclusions about electrodes. Now, you're going to say that a definition of an electrode can be a conductor which can easily carry electricity into or out of the cell, and the electrodes are going to be categorized into two. So electrodes include, one of them is going to be the anode and the other one is going to be the cathode. Now in your O-level, you are told that at the anode we have anions. So that means that for you to easily remember this, is that you must couple an with an. And at the cathode, we always have cations. So at the cathode, you must couple cats with cats. And therefore, you easily remember that at the cathode, we decompose the cations, or we reduce the cations in preference to the anions, and at the anode we deal with the anions in preference with the cations. So an together with cat is a simple prefix that you can be using to memorize anything about decomposition of electrolytic solutions at the cathode together with the anode. But sometimes we go ahead and then we ask you for the definition of the anode, because for you to be good at electrochemistry, you need to be having a good understanding of these two. So at the anode, or the electrode of the anode, you often find that it's going to be that electrode where oxidation takes place. And you should be knowing this, because when you're advancing in electrochemistry, we are going to look at redox reactions. So you need to know where oxidation takes place and where reduction is taking place. And that's how you're going to master electrochemical cells. Without knowing this, you are going to have difficulties in electrochemical cells. So the anode is going to be the electrode where our oxidation is going to take place, and the cathode is going to be that electrode where reduction is going to take place. So an anode, in simple terms, as we're summarizing your notes, is going to be the electrode where oxidation takes place, or the electrode where we have oxidation, and the cathode is going to be the electrode where we have reduction. I've said that this is very, very important when it comes to electrochemical cells, and you need to take it very, very seriously. Now let's look at some of the principles that are going to be involved under this topic of electrolysis, or what we call the selective discharge of ions, the cations together with the anions and the specific electrodes. So we're going to say that under similar conditions, when two or more ions or anions together with cations with a similar charge are going to be present in solution, for example, or for instance, the protons, sodium ions, or chlorides and hydroxide ions, one of them is going to be preferably selected for discharge as compared to the other present at the electrode, and the selection is going to depend on the following factors. Now remember that I said at the cathode we have reduction taking place, and the cathode discharges cations. The anode is where we have oxidation taking place, and it deals with anions. So for discharge to take place, the following factors are going to be put into consideration, and one of them is going to be the position of the ion in the electrochemical series, which we are going to look at in details, together with the concentration of the ions that are present in solution, and the nature of the electrode, that is being used in the electrolytic cell. Now let's first look deeper into the details about position of the ion in the electrochemical series. Now this is going to be our table that is going to be guiding us on the position of the respective ions, the cations together with the anions in the electrochemical series. But what you should know mostly is that the hydroxide ion is the last one, and in among anions is going to be, now for anions, when the arrow goes down, the increase of the ease at which that respective ion is going to be discharged. So according to this arrangement, the hydroxide ion is going to be discharged first as compared to the iodide ion, and the iodide ion will be discharged first as compared to the bromide ion. But most of the solutions, you are going to have your hydroxide ion to be existing in solution. So most of the solution we shall be considering discharge of the hydroxide ions, unless other factors become prominent that we looked at. For example, nature of the electrode or concentration of the ions that is present in solution. Like we shall look at the example under brine or sodium chloride solution. So for cations, the electrochemical series is as follows. If you look at this series, you often realize that it quite resembles the reactivity series being reversed from here to aluminium, and the other ones are going to be other cations, mainly transition metal cations. Now let's look at the examples that involve elaborative explanations. Now explaining position of the respective ions in the electrochemical series, you're going to look at electrolysis of sodium hydroxide solution, and you're going to be saying that consider solution having sodium hydroxide. In this solution, we are going to have the following cations. So the cations are going to be hydrogen ions, and hydrogen ions are going to be from water. Remember that sodium hydroxide solution is a solution containing water together with sodium hydroxide as a base. So also water ionizes to produce protons, and sodium hydroxide ionizes to produce sodium ions. So you're having two cations. And for us to discharge these cations, we're going to depend on the position of the respective cations in the electrochemical series. So if you consider hydrogen ions together with the sodium ions, you find that the hydrogen ion is going to be discharged in preference to the sodium ion at the cathode. Reason being, the hydrogen ion is at a lower than sodium in the electrochemical series, and therefore the observation that you're going to be seeing is going to be the hydrogen gas, which is going to be formed at the cathode. Remember that I told you at the cathode is where reduction takes place, and we deal specifically with cations. So protons are going to be discharged by addition of electrons to give us a colorless gas of hydrogen, which is going to be hydrogen gas. So the observation is effervescence of a colorless gas, and then the gas that will be formed, or the equation, is going to be hydrogen gas. So if you look at the electrolysis of the silver nitrate solution, the solution is going to contain anions of hydroxide. Now this hydroxide or the hydroxyl ions are going to be coming from water, and then the nitrate ions, which are going to come from the silver nitrate ions. But remember, I told you that the hydroxide ion is always going to be discharged because it's lower than any other anion in the electrochemical series, provided other factors do not convenience, like we're going to be looking at the respective examples. So we're going to say that the hydroxide ion is going to be discharged in preference to the nitrate ion. And the reason for that is because the hydroxide ion or the hydroxyl ion is lower than the nitrate ion in the electrochemical series, just like I gave you a sketch about that. So it's going to be discharged at the anode, since the anode is a site for oxidation. And remember that as anions, since they are negatively charged, for them to gain stability, they have to be oxidized. So anode is a site for oxidation, or it's an electrode where oxidation takes place, and it deals with mainly anions only. So the observation that's going to be seen is going to be effervescence of a colorless gas, and that colorless gas that is going to be formed is going to be the oxygen gas. So the equation that is going to be formed at the anode, we are going to look at the discharge of the hydroxide ions to give us effervescence of a colorless gas, which is going to be oxygen, together with electrons to balance up our equation. Equation balancing will follow the same criteria, like I've been emphasizing under the transition chemistry videos. I elaborated that in details. So I don't expect anyone on this platform to have challenges with equation balancing. So we are going to make a following note that the order of preferential discharge given in the table above is going to only apply for the discharge from aqueous solutions containing ions at comparable concentrations, probably about 1 molar. So sometimes exceptions arise as a result of large difference in concentration, as you're going to look at the elaborative examples and look at that in details, which is going to include other factors that you mentioned. So position of the ions in the electrochemical series, I hope, has been understood, and because it has been fully detailed and explained. Now, looking at other factors, you're going to be explaining the second factor, which was about concentration of the ions in solution. And this is mainly due to the electrolysis of the sodium chloride solution or concentrated sodium hydroxide solution, which is commonly known as brine. So brine is used for formation of chlorine gas, but it's also used for formation of sodium hydroxide as a result of electrolysis due to the effect of concentration. Now, just to give a general takeaway about this is that for electrolysis to take place or for any particular ion to be discharged either the anode or the cathode, there must be a high concentration of those respective ions that are going to be discharged in preference to the other ions. So for example, you're having concentrated sodium chloride solution. There must be a lot of chloride ions in solution for chloride ions to be discharged. That means that if chloride ions are going to be discharged, the hydroxide ions are not going to be discharged, but they are the ones which are supposed to be discharged according to the position of the ions in the electrochemical series. But since the chloride ions are present in huge concentration, they are going to be discharged in preference to the hydroxide ion, because the energy of discharge of the chloride ions is going to be less than that of discharge of the hydroxide ions. So the chloride ions end up being discharged in preference to the hydroxide ions. Now, looking at this, we are going to make a elaborative essay about it, and we're going to say that an ion present at a lower concentration is more difficult to discharge than an ion which is going to be present at a higher concentration. So the electrolysis of sodium chloride solution is going to liberate chlorine gas at the anode during the manufacture of chlorine gas. So this is because although the solution contains the anions of the hydroxide together with the chloride ions, the chloride ions are going to be discharged in preference to the hydroxide ion because the chloride ions are present in a very high concentration than the hydroxide ions, and therefore less energy is going to be required to discharge the chloride ions as compared to the energy that is required to discharge the hydroxide ions. So chloride ions are going to be discharged at the anode to give us the chlorine gas, which is going to be effervescence of a greenish yellow gas, which is the green gas because it's the only gas that carries that color in the laboratory. And the other thing is going to be that electrolysis of concentrated hydrochloric acid is going to liberate chlorine gas at the anode for the same reason as the case above. Because here, since hydrochloric acid is concentrated, that means that we shall have a lot of chloride ions in the solution which are going to be discharged in preference to the hydroxide ions because they are present in high concentration. Therefore, the energy that will be required to discharge the chloride ions is going to be less than the energy required to discharge the hydroxide ions. Now, just like you said, that this concentrated sodium chloride is also known as brine. So make sure that there are a lot of questions about this in the question bank. So make sure that you approach those questions with adequate vigor, knowing that you're going to pass because you have looked at it. So preparation of sodium hydroxide is also done using concentrated sodium chloride solution. There at the cathode, sodium ions are going to be discharged in preference to the hydrogen ions from water. And therefore, since sodium ions are present in high concentration, the energy of discharge is going to be lower than the energy of discharge of the hydrogen ions. So sodium ions are going to be discharged at the cathode, forming sodium forming sodium metals. Now these sodium metals react with the material cathode, which we have used to form sodium amalgam, which dissolves in water to give you the sodium hydroxide that you are preparing. I hope that is well detailed and well explained. Now let's look at the nature of the electrode as another factor affecting electrolysis of ions in the electrochemical cells or electrolytic cells. So I'm going to say that inert electrodes such as platinum may not affect the products of electrolysis, but however, some electrodes may affect the products of electrolysis. For example, let's look at the preparation of copper. Now we are going to explain the nature of electrode in two parts. So we are going to first look at preparation of copper or using copper as the electrodes. We are going to look at it under the next explanation. Let's first look at the electrolysis of sodium chloride, which is preparation of sodium hydroxide that I've just been explaining using brine or concentrated solution of sodium chloride, using the cathodes of platinum, using platinum cathode and also mercury. So this was supposed to be. So you're going to compare when you're electrolyzing sodium chloride using one, we are going to look at platinum cathode, and also two, we look at mercury cathode, and we look at the products that are going to be, or the variance that's going to be present in the cathodes, in the respective cathodes. So when you use platinum, remember that I told you platinum is an inert electrode, so there is no reaction that takes place with it. So when platinum cathode is used, the hydrogen ions are going to be discharged in preference to the sodium ions, and the reason is because of the position of the electrochemical series. And you're going to say that the hydrogen ion is lower than the sodium ion in the electrochemical series, and therefore hydrogen is going to be discharged at the cathode or at the platinum cathode in preference to the sodium ions. So we shall form an equation, or we shall see effervescence of a catalyst gas at the cathode as a result of hydrogen being formed. But however, when we use a mercury cathode, like during preparation of sodium hydroxide, the sodium ions are going to be discharged in preference to the hydrogen ions. And this is because the discharge of the sodium ion is going to require less energy than the discharge of the hydrogen ions. So in case the electrochemical series does not work, we explain the other things, or we reason out discharge of the respective ion according to energy. So in case electrochemical series, or the position of the ion in the electrochemical series is not applying, you explain in terms of energy that this ion is being discharged in preference to the other because its discharge requires less energy as compared to the other ion which you are comparing it with. So what you do is that after sodium being formed at the cathode or being discharged at the cathode, is that the sodium reacts with the mercury to form sodium amalgam. That's why we are saying that sodium amalgam is therefore formed at the mercury cathode by the reaction between the sodium together with the mercury cathode that you have used. So first is going to be the discharge, and after the discharge, the sodium atom or the sodium that is being formed reacts with the mercury to give us sodium amalgam. Now for you to get sodium hydroxide, we get this sodium amalgam and then we dissolve it in water. And that's how you form sodium hydroxide. It's a very common question under paper 1 of chemistry. So looking at part B, let's look at electrolysis of copper to sulfate, one using the platinum anode and two using the copper anode. Just like we said, platinum anode is inert, but the copper anode is not inert. So let's look at the reactions or the electrolytic reactions that are going to take place in such an electrolytic cell. So using the platinum anode, the hydroxide ions are going to be discharged in preference to the sulfate ions because now here when you're using the platinum anode, you're going to consider a position of the electrochemical series. So the reason for that is because the hydroxide ion is lower than the sulfate ion in the electrochemical series. So therefore, oxygen gas is going to be evolved at the platinum anode. So the observation will be effervescence of a colorless gas. However, the solution at the anode is going to become acidic due to the reaction between the hydrogen ions which have been left together with the sulfate ions that are going to be left undischarged, forming sulfuric acid that's going to make the resultant solution acidic. sometimes they ask this in missed questions that involve explanations. So first, at the anode, we see oxidation of the hydroxide ions to give us the oxygen gas together with water and the electrons to balance up our equation. And then the sulfate ions being undischarged, they are going to react with the protons that are from water after giving off the hydroxide ions, forming the sulfuric acid, making the resultant electrolytic solution acidic. And therefore, one of the observations you see is that the litmus paper, the blue litmus paper will turn to red, indicating that the electrolytic solution is now acidic. So you're going to say that, however, when a copper anode is being used, we are not going to discharge either the hydroxide ions nor the sulfate ions. But however, the copper anode itself is going to dissolve in this solution, forming copper 2 ions. So the electrolysis is going to be merely a transfer of copper from the anode to the cathode, because it's the anode that is going to be dissolving to give us the copper 2 ions. And remember that we say that at the cathode is where ions or cations get discharged. So these cations of copper that have been formed in solution as a result of dissolution of the anode, they are going to migrate to the cathode, and we discharge them as copper. And this is what you use under extraction of copper when you're concluding the process. And we say that we get pure copper by electrolysis, and all those videos about transition chemistry have been uploaded still on this channel. So let's look at the laws that are going to be involved in electrolysis. So one of them is going to be the Faraday's first law of electrolysis, and it's going to state that the mass of the substance that is going to be liberated at an electrode during electrolysis is going to be directly proportional to the quantity of electricity that is going to pass through that electrolyte. So mass of a substance that is going to be liberated at an electrode during electrolysis is simply directly proportional to the quantity of electricity passing through that electrolyte at that time or at a given temperature. So let's look at the other law. So to put the law in use, or to put the law in illustration, we are going to say that mass of a substance that's going to be formed is going to be directly proportional to the quantity of electricity passing through it. But you get quantity of electricity simply by getting amperes or electricity or electric current in amperes multiplied by time. And we therefore conclude that M being there is going to be directly proportional to IT. But for us to remove this proportional constant, we replace it with the proportionality constant that is used in electrolysis, which is denoted by capital E. So M is going to be equal to capital E IT. So we have given the key for that, where the M is going to be the mass of the substance consumed or produced at the electrode, and Q is going to be the quantity of electricity or the quantity of charge that is passing through that electrolyte, but it's going to be measured in coulombs. And then I is going to be the current that is going to be measured in amperes, and then T is going to be the time that is going to be measured in seconds for which the current was passed, or for which the current or the electricity was passed through the solution that is being decomposed, or the molten substance that is being decomposed. Now E, just like we said, is going to be called the proportionality constant, and it's also called the electrochemical equivalent, for as long as you write it in terms of capital letters. Now the second law of Faraday's of electrolysis is going to state that the quantity of electricity that is going to be required to liberate any 1 mole of an element is going to be directly proportional to the charge number of its ion. Quantity of electricity required to liberate 1 mole of any element is going to be proportional to the charge number of its ion. So looking at that, we're going to say that the charge number of an ion is going to be represented by Z, and the number of the positive or negative charges which the ion possesses is also going to be represented by Z. So it can be positive or it can be negative. For example, if you're having a proton, remember that the proton is written as capital H, and then the charge on it is going to be +1, but we just write plus. So Z here is going to be equal to 1 without carrying any charge, because and can either be positive or negative. So we simply don't carry the charges. So if you're having if you're having cations, there's no need to indicate that it's going to be positive one. And then, but for anions, it's going to be required for you to indicate that's negative. But for cations, don't indicate any charge on it when you're finding the Z. So if you look at aluminium, the charge on it is going to be positive 3. So Z is going to be simply 3. If you look at the chloride ion, the charge on it is negative 1. So Z is going to be equal to negative 1. Here it's relevant to show the sign because it's an anion. So for the oxide ions, Z or the charge is going to be equal to negative 2. So we're going to say that the magnitude of the charge number, which is going to be Z, is usually equal to the number of moles of electrons that are going to be required for the ion to be discharged. For example, for us to discharge aluminium, we are going to need 3 electrons. That's what we mean. So if at all you're having positive 3 here, for ion to be discharged, we are going to need 3 moles of electrons to discharge the cation of aluminium for us to get the aluminium on our cathode. Now let's start the calculations that are going to be involving the laws or the 2 laws that we have covered. So we're going to look at the calculations that are going to be involved in electrolysis, and looking at the examples, we are going to look at a few of them. So we're going to calculate the quantity of electricity that is going to be required to deposit 40.5 grams of aluminium during electrolysis of a solution of aluminium ions, provided 1 farad is going to be equal to 96,500 coulombs, together with aluminium having the atomic mass of 27. So summarizing that out, we don't have our charge or the quantity of electricity, and then the mass of the given compound they're talking about to be electrolyzed is going to be 40.5 grams. So first of all, we have to write our equation to indicate the discharge of the aluminium ion forming aluminium. So aluminium ion is going to need 3 electrons to be discharged to form the aluminium solid. So according to the equation, 1 mole of aluminium is deposited by 3 moles of electrons. But remember that electrons are equivalent to the charge that is required. So 1 electron carries 96,500 coulombs. What about the 3 moles of electrons that you are going to be using? So that's why you're going to have 3 multiplied by 96,500. And since they give us mass, we convert the mole that is of aluminium we are having in terms of mass, so that we can relate them properly. So 1 mole is always equivalent to the atomic mass or the molecular mass of any given element or compound. So for aluminium, the molecular mass or the relative molecular mass is going to be 1 times 27, so which is equivalent to 1 mole. And for us to convert these moles of electrons to charge, which is required, the quantity of charge, you multiply each mole of electron by 96,500. So it's going to be 3 times 96,500 coulombs of charge. Then what about, so that means that these grams or 1 mole is giving us this quantity of charge. Then what about the given mass, which was 40.5 grams? So 40.5 grams is going to deposit 3 times 96,500 multiplied by 40.5 divided by 27 coulombs of charge, and you're going to end up with this charge, which is going to be 434,250 coulombs of charge as the required answer. So in the next number, we are going to look at when current is being passed through a solution of silver nitrate solution for 10 minutes. So the time which was given here is 10, but remember that our time must be in terms of seconds. And the given mass here was given as 0.54 grams of silver. Since they gave us mass, that means that you need to convert the moles that you get in your equation to mass. So these ones are going to be deposited at the cathode. So we are supposed to calculate for the current. That is passing through that solution, provided 1 farad is equal to 96,500 and is present in 1 mole of electrons. But that of silver, atomic mass of silver is equal to 108. So let's look at the responsive calculations. Now there was a pairing up error, or there was an editing error. The solution that was presented was for number 3, and you are handling number 2. So make sure that you skip that step, or you try that number, and then you present your solutions in the WhatsApp group that you have created. I'll be analyzing it, so I'll be giving a solution for that. So this solution was for number 3. So let's just proceed with number 4. So number 4 is saying that calculate the mass of lead that is going to be deposited at the cathode during electrolysis when a current of 1.5 amperes flows through molten lead to bromide for 20 minutes, provided the atomic mass for lead is going to be 207. So first is to summarize out what the question has given you. So our current, you're having it as 1.5 amperes. Time we are given in terms of minutes. But remember, time has to be converted to seconds. That's why when you are saying that charge is equal to current times time, we converted our amperes or our time in terms of seconds by simply saying 20 times 60. So the charge you got it as 1800 coulombs. So after that, you write the equation of discharge, and then we read this equation, or we write out the statement leading to this equation. So according to this statement, 2 moles of electrons deposited 1 mole of lead. But to convert the moles, you have to convert the moles. Remember that each 1 mole is equivalent to 1 farad, which is the same as 96,500 coulombs. So 2 moles is the same as 2 times 96,500 coulombs, and therefore the charge that is going to be deposited, we have to convert this mole in terms of mass, because the question is a need of mass. So 1 mole is equivalent to the relative molecular mass of any element or substance. Solid in terms of mass is the same as 1 times 207. So what about the charge that we calculated, which was 1800? Because this charge gives us the molecular mass. What about the charge that we calculated? Is the one that is going to give us the mass of lead that was deposited, because it's the charge that passed through that electrolyte. So 1800 coulombs is going to give us the following expression that is going to give us a mass of 1.931 grams of lead, and that was the mass of lead that was deposited at the cathode. Now quickly let's go through question 5. Now question 6 will be your self-assessment question, so that you can look and see where the solutions came about. I gave you the solutions, but you can first try it on your own without looking at the screens. So number 5 is saying that an electric current was passed through a solution containing copper to sulfate and electrolyzed using platinum electrodes for 1 hour. So time is equal to 1 hour, but remember that this hour has to be converted to seconds. So when you're calculating, so number 1, you're going to calculate the strength of the current that is used to deposit 0.106 grams of copper at the cathode. But now to do this, since we are given mass, that means that we need atomic mass of copper. And 1 mole of electrons is equal to 1 farad. 1 farad is equal to 96,500. So you have to write the equation for that first. We have already summarized that. So for us to deposit copper, we need 2 moles of electrons. For us to deposit 1 mole of copper. So since they took the question give us grams of copper, that means that you're going to start with copper this side, and then what they need, which is the current in terms of moles of electrons, it must be this side. So 1 mole of copper was deposited by 2 moles of electrons according to the equation. So we have to convert the electrons to charge also the 1 mole to mass. So 1 mole is equivalent to the atomic mass of copper, which is the same as 1 times 63.4 according to the periodic table. So it's going to be deposited by, to convert the moles of electrons to charge, we are going to get 2 times 96,500 in terms of coulombs of charge. Then what about the given mass, which was given in the question, which was 0.106? So it's going to give us a charge of 322.68 coulombs. Now looking at the charge required, we are going to come and say that therefore charge is equal to 322.68 coulombs, but charge at the same time is the same as IT, or current in amperes times time in seconds. But for current in amperes, we don't know it, and it's the one which we are supposed to calculate for. The charge you have already got it as 322.68. So current in amperes times time we had 1 hour. So for us to convert this 1 hour into seconds, we have to get the 60, you have to multiply it by 60 to convert it to minutes. After converting it to minutes, you multiply it by another 60 to convert it in seconds. And you make I the subject, which is going to be 322.68 divided by 3,600, and you're going to end up with your current in amperes to be 0.0896, which was required by the equation as of part A. Now looking at part B, you have been told that if the electric cell above in the series was in the series with the silver nitrate cell, calculate the mass of the silver that is going to be deposited on the cathode of the second cell. So first you are going to summarize all the same cases. Ampere, current in amperes, you have calculated it to be this, and then time was given in 1 hour, and then the mass we don't know it. So you're supposed to calculate for the mass of silver that is deposited. So first of all, we have to write out, now the quantity of electricity is going to remain the same since the cells are present in series. I hope you remember your O-level physics. So charge or quantity of electricity passing through those cells is going to remain the same, which is 322.68 coulombs. So first, since they talked about silver, we are going to write an equation for discharge of silver. And since they talked about mass, we shall put moles this side because it's what we need to convert into mass. And then since we have the charge already, we shall put moles of electron this side because 1 mole of electron is equivalent to the Faraday's constant, which is 96,500. So silver ions are discharged to give us the silver solids. But 1 mole of electron to convert it into charge, the same as 1 times 96,500 coulombs of charge to be deposited by 1 mole of silver, which is equivalent to the relative molecular mass of it, which is 108. So what about the charge that we calculated above, which was 322.68 coulombs of charge? Is going to deposit how many grams of silver? And calculating and substituting everything in the calculator is going to give you 0.361 grams of silver to be the mass of silver that was deposited on the cathode of the second cell. Now this is going to be your assessment exercise. You must read through this question. I know there are very less in the question bank, so try to read through this question and try to follow it up and see how these solutions were made, and then comment about how you understood it. If you had any issues, I told you issues will be subjected to the WhatsApp groups that have been already created, and the link will be provided in this channel. So pause the video and try to analyze the question and how the solutions came about by yourself in about 30 seconds. And now we are going to be concluding electrolysis by looking at some of the applications or the fields where it can be applied at the industrial level. So when you're talking about electrolysis, elements like potassium, calcium, sodium, magnesium, among others, are very reactive and therefore they can be found as free elements. So they are extracted by the electrolysis process, as we looked at how we can extract some of them under the transition metals videos. So potassium is extracted from fused potassium hydroxide, sodium is extracted from molten sodium chloride, and calcium from calcium chloride together with aluminium from bauxite, and we already looked at this. Now let's look at the extraction of sodium by electrolysis from molten sodium chloride, which is the same as brine. And you're going to be using the Downey's process. So the same process is used to manufacture chlorine, but you have already looked at that under the previous notes, where we are talking about, or where we are explaining, effect of concentration of ions in the electrolytic cells. So with that, you're going to say that sodium is going to be extracted by electrolysis of molten sodium chloride, which is also known as brine in the Downey's cell. So a carbon anode is going to be used and anion cathodes are going to be used and separated from each other simply using an iron gauze diaphragm. Now I didn't provide a diagram because it's not required. So calcium chloride is going to be added to the electrolyte to lower its melting point of sodium chloride from about 800 degrees Celsius to about 600 degrees Celsius. So what you're going to see is sodium chloride is going to be decomposed by the electric current to form the sodium ions and the chloride ions. So sodium chloride decomposes to give us sodium ions together with the chloride ions. So in decomposition, the sodium ions are going to be preferably discharged at the cathode in preference to the hydrogen ions from the water, and the reason for that is because the sodium ions are present in higher concentrations because we are using molten sodium chloride. So at the temperature it's going to be used forming sodium at the cathode. So at the cathode, sodium is going to be discharged forming the sodium, or giving off sodium atoms in terms of liquid. So the chloride ions are going to migrate to the anode, forming the chlorine gas. So chloride ions are going to be discharged in preference to the hydroxide ions because they are present in high concentrations, and therefore the energy of their discharge is going to be much lower than that for the discharge of the hydroxide ions that may be coming from water, which escapes from the cell. So we are going to see at the anode you'll be seeing bubbles of a greenish yellow gas, so effervescence of a greenish yellow gas. Now we can also look at the anodization of aluminium as another application of electrolysis, and here we look at aluminium being normally covered by a thin coating of aluminium oxide, and this is very common among iron sheets. And we do this to protect it from corrosion and to make it resistant from chemical attacks. That's one of the reasons why some of the aluminium made iron sheets last longer. So the thickness of the oxide layer is going to be increased by electrolyzing it with the sulfuric acid or with chromic acid together with the aluminium made material of the anode, and the oxygen is going to be liberated at the anode. The oxygen that will be liberated at the anode will react with aluminium to form a protective layer of aluminium oxide that will prevent it from being affected by, for example, iron sheets. If at all you get an aluminium made iron sheet and then you crack it somewhere, the oxygen that is present in the atmosphere reacts with that aluminium, forming a coating in the cracked area, forming aluminium oxide, which further prevents it from the hydrated environment, preventing it from corrosion, or preventing rusting from proceeding. So the anode hydroxides are going to be discharged, giving us oxygen. The oxygen that is formed reacts with aluminium to give us aluminium oxide, which is a further coating, preventing rusting. Now the other application is going to be electroplating, and we're going to say that this is the electrical coating of one metal with another metal to make it resistant to corrosion or rusting and improve its appearance. So the metal to be electrolyzed is going to be made of the cathode, and the electroplating metal made of the anode, and the electrolyte must contain a solution of the ions of the electroplating material. However, this is just an elaborative part of electroplating, but what you should know here is that you need to know at least a minimum of 2 applications of electrolysis. So one of them is electroplating, and another one is going to be anodization of aluminium, and the other one will be formation of sodium from brine solution, or from concentrated sodium chloride, or from molten sodium chloride, either of the 3. Now let's go over the other applications, which are just going to be a little bit minor. So the other applications, one of them is going to be extraction of aluminium by electrolysis of molten aluminium oxide, and also manufacture of sodium hydroxide by electrolysis of brine, which I've already talked about, using mercury cell, which is known as the Castina Kellner's cell, or the diaphragm cell, which I've just talked about. So the same process can also be done as well during the manufacture of chlorine. We have already talked about this in details. So the other process is going to be manufacture of sodium chlorate together with sodium chlorate 5. Chlorate 1 is where we have this compound, and the chlorate 5 is where we have this ion. You looked at this in group 7, which was a video uploaded on this channel. So you can go over this, but it's not relevant or required, but because on the syllabus we no longer examine it, so there's no need for us to be reviewing it. Now this brings us to the end of this video. Your advice: share the video to your friends, subscribe to the channel, and like the video so that it can be posted to other friends that are in need of the videos. So like I said, make sure that you present your concerns in the WhatsApp group. Stop clogging my inbox, because that will be I may reply you, but you may get delayed replies. Make sure that you present your concerns in the groups that are being formed, and make sure that you like the video so that also other students may pop it up. So see you in the next video, where we are going to be going deeper into the topic of electrolysis. This was an introduction video. I hope you understood, and if you didn't understood or you're lacking anywhere, try to make sure that your concern is addressed in the comment section. I'll be reviewing everything, and I'll be revising on the areas that you're lacking. So see you in the next video.